Ever stretched a photo on your phone and watched it warp? Faces stretching sideways, straight lines bending? Take any grid of pixels, pull it unevenly, and it immediately looks unstructured. But hidden inside that distorted image is a set of directions that remain perpendicular even after the stretch. How does a random uneven pull preserve this perpendicularity? To find out, we must look at how matrices manipulate space. Instead of seeing numbers, we must visualize the fundamental geometry underneath the math. A matrix A is not just a grid of numbers. It is a machine that transforms space. Apply A to a coordinate grid, and it stretches, shears, and rotates the entire system. Usually, this looks complex, with angles warping and distances changing inconsistently. Linear algebra tries to find order in this complexity. Eigenvectors can achieve this, but only for special square matrices. Most square matrices lack perpendicular eigenvectors, and rectangular matrices lack them entirely. We need a more universal tool. Let us make this everyday intuition geometrically precise. Imagine rolling out a circular piece of pizza dough. Assuming a linear stretch, that circle deforms into an ellipse. Consider a simple 2x2 matrix with a top row of 2, 0 and a bottom row of 1, 1. Applying this to a unit circle stretches it, mapping the original perpendicular axes directly to the major and minor axes of the new ellipse. These axes correspond to the singular values, which we calculate later. Every single linear transformation can be broken down into 3 sequential geometric steps. Instead of viewing the matrix A as a single distortion, singular value decomposition breaks it apart. It tells us we can achieve the exact same result by rotating our coordinate system, stretching it along the axes, and then rotating it once more. In 2 dimensions, this means a circle is rotated so its key directions align with our stretch axes, scaled perfectly into an ellipse, and rotated to its final state. The algebra of this process is the equation A equals U times sigma times V transpose. Here, V transpose is an orthogonal matrix performing the first rotation, aligning our input vectors with the principal stretching directions. Sigma is a diagonal matrix of singular values, representing the exact stretch factors along those axes. Finally, U is another orthogonal matrix performing the final rotation into the output space. This exact sequence breaks any matrix into 3 physical actions. Let us take a non-square matrix A with a top row of 3, 2, 2, and a bottom row of 2, 3, minus 2. To find the columns of V and U, we analyze the symmetric matrices A transpose A and AA transpose. The eigenvectors of A transpose A give the right singular vectors for V, and AA transpose provides the left singular vectors for U. When we multiply our matrix A by a column of V, it lands exactly on the corresponding U column, scaled exactly by its specific singular value. For our matrix, this cross-verification holds true, yielding A times V1 equals 5U1, and A times V2 equals 3U2. Our dominant singular values are sigma 1 equals 5 and sigma 2 equals 3. Since our matrix is 2 by 3, its maximum rank is 2. Consequently, the third singular value, sigma 3, is exactly 0. This illustrates exactly how SVD handles non-square spaces. The third dimension completely collapses, proving mathematically why certain vectors vanish into the null space. The diagonal entries of sigma, the singular values, are always sorted in descending order, from largest to smallest. They represent the dominance and impact of each singular vector. In data science, these values tell us exactly how much variance or information each axis captures. The first few singular values are usually large, while the rest quickly drop close to 0. This means most of the matrices transforming power is concentrated in a few key directions, capturing the essential data structure. Discarding the smallest values simplifies the data. Keeping only the dominant sigma 1 yields a rank 1 approximation, A1. Subtracting this from our original matrix leaves an error matrix with values 0.5, minus 0.5, 2, over minus 0.5, 0.5, minus 2. The total magnitude of this error is exactly the square root of 9, or 3. The error introduced by dropping sigma 2 equals the value of sigma 2.
This mathematically guaranteed truncation is how image compression works. We know that SVD breaks any linear transformation down into an initial rotation, a stretch, and a final rotation. But why is this combination mathematically guaranteed to work for every matrix, regardless of its dimensions? The geometric proof of this concept reveals a direct symmetry between input and output spaces. To see this visual proof and understand why this process applies across all of linear algebra, click on the next video. Every matrix is a rotation, a stretch, and another rotation.